Hi, so welcome to week 2 of Physics 30. This week is definitely bigger than last week. Last week was meant more to kind of just get us used to this online format. This week we're going to be using our hands to kind of come up with hand rules to determine the direction of magnetic fields, magnetic forces. The one thing I would suggest before this week is watch this Veritasium video here. Linking electricity to magnetism. There is in the Google Classroom it's posted under introduction, but we watched the one in last week's assignment dealing with why things are permanent magnets. This one is talking about how moving charges causes things to behave like magnets. This week we're going to be dealing with hand rules. So hand rules. We use our hands because our hands are great because there's 3 different surfaces, right? We have our thumbs, which are perpendicular to our fingers, which is perpendicular to our palms. And you really need all 3 of those surfaces because now that we're dealing with magnetic forces and moving charges and external magnetic fields, these things are all perpendicular to each other. So we're going to be looking at 3 different hand rules this week, which allows us to determine direction of magnetic fields, the direction that a charge is moving, direction of magnetic force. Now, when we're talking about these hand rules, there's 2 important things to note. Number 1 is that if we're ever talking about anything negative, so electrons, electron flow, or anything negative, and that could even be things like negative ions, like maybe chloride ions, we are going to be using our left hand. The other thing to note is we're talking about anything positive, so protons, we could even have alpha particles, we could have positive ions like sodium ions, or conventional current. Now remember, conventional current is Benjamin Franklin, he kind of got it all twisted and he talked about the movement of positive charge. But anything that is positive, we're going to be using our right hand. Now, most stuff in Physics 30 will be dealing with left-hand stuff. When we talk about current, most of the time, unless it's specified, we're dealing with electron flow from negative to positive. But yeah, so let's talk about the first of these rules. Or I guess first let's talk about some other things when it comes to directions. One thing that we do need is to be able to express things as going towards us or away from us. So there are these 2 new ways to kind of deal with vector directions. I like to think about it as like an arrow, kind of like that. If the arrow is going into the page, I'm going to see kind of the feathers there. If it's coming out of the page, I'm going to see the tip of the arrow coming at me. So there's these 2 directions that we do need to be familiar with. An X means that it's going into the page. A circle or a dot, I guess, means it's coming out of the page. And thinking about an arrow is a useful way to visualize that. So the first hand rule. So this applies to straight wires. So the first hand rule says that when we're talking about straight wires, so this could be a straight wire. Here, maybe electrons are going that way. Or I maybe have a straight wire like this, where the electrons are coming out of the page. When I talk about a straight wire, the first hand rule says that my thumb goes the direction that the current is flowing. My fingers wrap around the direction of the external magnetic field. Okay, so here's the first hand rule. The first hand rule has to do with straight wires. Now, typically in Physics 30, we're going to be using our left hand because we're going to talk about electrons. Electrons go from the negative side. Now, I have a power supply over here, but electrons come from the negative side. That's this black wire. Travel through the wire and then go to the positive side. So the electrons are traveling this way. So the first hand rule says my thumb goes the direction the electrons are moving. What my hand does is it curls under. So if this is the wire, okay, here's the direction the electrons are moving. My hand curls around the direction of the magnetic field. So there is a circular magnetic field around the wire. So underneath it would be pointing that way, up top it would be pointing that way. So we can test that. So if I turn on the power supply, so this is underneath, I would expect, because the charges are going that way, that I would curl under the wire and the direction of the magnetic field would be to the right, and it is, right? When I turn it on, I see the needle goes to the right. If I were to put that compass on top of the wire, now I would expect it would go to the left. Turn it on, and it does. So on the top it goes that way, and then on the bottom, underneath, it goes the other way. So it goes that way on the bottom, and then the other way on the top. So that is my first hand rule. So for straight wires, my thumb goes the direction that the charge is going. So it goes from negative to positive. And my hand curls around the direction of the magnetic field. So there's a circular magnetic field around the wire, and that's the direction that my hand curls. Here's another question. Maybe pause the video and try it on your own. What is the direction of the magnetic field around this wire? And actually, even to make it a little bit better, let's put it next to this one. And let's identify if these two wires are going to attract or repel. So pause the video now and answer it. Okay, so this one on the left is going into the page. So if I put my left, I'm talking left hand because I'm talking electrons. If I put my thumb into the page, my fingers are going to curl around this direction. So that is the direction of the external magnetic field. If I look at this second one, now my thumb's coming out of the page, and my fingers would curl around this direction, the direction of the external magnetic field. Now, to determine whether it attracts or repels, it is easier to think of these magnetic fields as being tiny magnets. So if I were to have two tiny magnets there, I know the magnetic field would come out from north and go into south. So those magnetic fields are orientated that way. And I know that if I had two magnets like that come together, they would repel. So these two wires would repel each other. That's the first hand rule. Charges. The second hand rule now deals with solenoids. Solenoids are just a fancy way of saying coils. Now, it could be a coil like this could be a coil. Or it could even be just a circuit, a circular circuit like that. That could also be a coil, like maybe that's positive, negative, negative, positive. Those are kind of two other ways to kind of picture a solenoid. Now the solenoid hand rule now, our fingers are the direction that the electrons are moving, and our thumb points in the direction of the north end of the solenoid as if there was a bar magnet inside. So the second hand rule has to do with coiled wires. So this is a coil. I taped it just to this thing just in order for it to stay in place. Now, coils do not necessarily need to have something wrapped around them. Like this could even be a coil as well, right? If electrons travel around the outside that tube, it's a circular path. Or even it could be as simple as, if I have something like this, this could behave as a coil as well. It just wouldn't be as strong. So I have a circular path that the charges are moving. So that would also behave like a coil. Now, what the second hand rule says, so now I kind of switch around the parts of my hand a bit. So the second hand rule says that my fingers curl around the direction that the charge is moving. So now my fingers are the direction of the charge and where it's going, and my thumb points to the north end of a magnet as if there was a permanent magnet inside of this coil. So this is negative and this is positive. So what the second hand rule says is my fingers curl over. So because the electron flow is over this coil and then it comes underneath, my fingers curl that way because that's the direction that the electrons are moving. What that means is that inside of this coil now, this would be the north end of a magnet. So it would behave like there's a permanent magnet here, and this would be the north end, so this would be the south end. If I were to use this probe to test it, so once I turn it on, okay, I'll turn it on. So I look inside there, you can see that, so this is maybe a little bit too small, but there is a So inside, that blue one goes away. Oh. So inside, it goes out from north. And then on this side, the red arrow points in. Right, so this is the south end. My fingers curl over. There's north, out from north, into south. And then as we go around the coil, you see that it follows just like a permanent magnet. The magnetic field lines are out from north and towards south. So it goes out from north towards south. I'll turn it off and then hook it up the other way. So now we would expect it to be flipped. If I look at this now my fingers are curling under. So this is negative, this is positive. So my fingers are curling under that coil. So that means this would be the north end, this would be the south end. And so I'd expect the magnetic field lines to be out from north, wrapping around, and then into south. So I turn it on. Now you see that it's flipped. It's going out from north. It wraps around, so over top. Now it follows the direction of that magnetic field out from the north. And then at the bottom here is now going towards south. So this is the south pole, this is the north pole, it wraps around. That's the second hand rule for coiled wires. Now it can even be, something like this. Maybe it's orientated this way, where now I have, okay, the direction of the the direction of the electrons is this way around the coil. That means this is the north end. When I stick that in there, sure enough, it's the north end. If we watch it go all the way down, it doesn't flip. So the direction of the magnetic field inside is just like if it were a permanent magnet. It's always that same direction. It's coming out. And then it flips around and follows the direction on the magnetic field on the outside, out from north and towards south. In these previous examples, we just moving and they're producing magnetic. The third hand rule is the one that probably after this week we use more often than not, because now this is dealing with kind of three parts. This is now dealing with charges moving through external magnetic fields. In this situation now, we have charges moving through a magnetic field. And because moving charges produce a magnetic field and we have an external magnetic field, they're going to interact and we're going to have a magnetic force. So these questions deal with kind of three different parts of our hand. Our thumb is the direction that the charge is moving. So we just do kind of palm up, just like this picture shows with this hand. Our thumb is the direction that the charge is moving. Our fingers point the direction of the external magnetic field. And again, that's where a compass would point. So where would a compass needle point? That's the direction our fingers are going. So out from north towards south, just like a compass. And then our palm is the magnetic force. So here this palm is facing me. This magnetic force would be coming out of the page towards me. So we have those three parts. We have our thumb going the direction that the charge is moving, our fingers being the direction of the external magnetic field, and then our palm is the force, which is easy to remember because it's a push. So where is our palm pushing? That's the direction that the force would be. So in this diagram, we have some moving charges here. These moving charges are going into the page. So I would put my hand like this. My thumb would go into the page. My fingers would be pointing to the right because this is the direction of the external magnetic field. A compass would point that way if it was in between. So my fingers are pointing that way. And my palm is left facing up. Now, your hand should kind of look like this, like in that photo video. I found some stock photo online. So the thumb is going into the page. Fingers are going the direction of the external magnetic field. My palm now is the direction of this magnetic force. So there will be a force acting on that wire, and this wire will experience a force up. we need to think about kind of what part of our hands are facing. So we're going to use our left hand. We see the electrons are going from here when the switch is closed. So my thumb should be pointing up because that's the direction that the electrons are going to be moving through that aluminum rod. My fingers are the direction of the external magnetic field. I see the north end is here, the south is there. So in between the horseshoe magnet, my fingers should be going into the page. So my thumb should be up, fingers going into the page, which means my palm is facing to the right. So when I turn it on, that aluminum rod is going to go away from the retort stand, the direction of the magnetic force. This question now actually involves two hand rules. The first place I need to start is with this electromagnet, and I need to use my second hand rule. I know that the electrons are going under here, so negative to positive, they're coming under and then curling over. So my hand needs to be facing to the right. I'm using my left hand because I'm dealing with electrons. It's curling over, and that means my palm is facing up. So this is the north end, and this is the south end of the electromagnet. Now the other thing I need then is the direction of that magnetic field, which on the outside would look like this, right? Into south, out from north. So there's the electromagnet. Then I can deal with that electron gun. So now when I'm looking down here at that electron beam, so I have the electrons are moving in that direction. That's the direction my thumb is going. My fingers, now the direction of the external magnetic field, need to be pointing up. So my thumb is going in the direction of the electron beam. Fingers are pointing up because a compass at that point would be pointing to the south end of that electromagnet. And my palm then would be facing to the right. So there is going to be a force on that electron beam, and that's going to deflect it to 4. In this question now, I'm dealing with positive particles. So in the mass spectrometer, so that's the top one, I want to know the direction of the magnetic field. So here I am dealing with a type of question that we'll see a bunch, but when I look at, I'm using my third hand rule, I'm using my right hand because these are protons. So this now I need to be using my right hand because these are positive particles. My thumb is facing this direction. Now you'll notice that that velocity is changing. We did centripetal force in physics 20. My thumb now is the direction of that beam is traveling. The other thing I know is the direction of the force. We know that the direction of the force is towards the center when things are traveling in this shape. So my palm should be facing to the center. My thumb is the direction that the protons are moving. And so that means that my fingers now are pointing out of the page. So the direction of this external magnetic field is out of the page.